Okay, so now let us have a look at the entanglement of two particular physical systems, namely two two-level systems. This will indeed turn out to be not too complicated. So in our normal description, the quantum state of such a collection of two two-level systems would be written in Dirac notation by just enumerating all the possible states of the two systems, looking at all the combinations, and then making a general superposition out of this. And we also transformed this and interpreted this as a vector with four components: alpha, beta, gamma, and delta. Now, in such a pure state, the density matrix, when we denote this here as psi, then the corresponding density matrix would just be psi, psi dagger. And that would be the density matrix of a composed system of this sort in a pure state. And we can simply work this out. And then we find the following structure, which is very simple. And I'm going to write it out even completely. So in these rows, you have alpha, beta, gamma, and delta. And in the columns, you have alpha complex conjugate, beta complex conjugate, gamma complex conjugate, and delta complex conjugate. And our subdivision into blocks just breaks this 4x4 matrix down into 4 2x2 matrices. And for convenience, I'm going to denote these blocks as A, B, C, D. Now, this is the general form of a quantum state, the general superposition of all the different possible states of the two systems, all these different states. But let us next first have a look at how a separable state would look like. So we have one state of the first system, which I'm going to denote as chi naught naught plus chi 1 1. And another state for the second part of the system, which has amplitudes phi naught and phi 1. And first of all, we can simply look what happens when we just multiply these states. This gives us a particular class of states in the composed systems where we can assign individual states to the different parts of the system, a state chi and a state phi. So this is the case of a separable system. And we can simply multiply everything out, and then we find the coefficients chi naught and phi naught multiplied in front of the state 0, 0, just by this product here, and chi naught phi 1 in front of 0, 1, chi 1 phi naught in front of the state 1, 0, and chi 1 phi 1 in front of the state 1, 1. So as a vector, this corresponds to a vector with components chi naught phi naught, chi naught phi 1, chi 1 phi naught, chi 1 phi 1. And if you think about this as two smaller vectors, then these two vectors are indeed proportional to each other, just multiplied by different numbers chi naught and chi 1 in both cases, just as we had in the general case. And moreover, we can now give a quantitative criterion to decide whether a quantum state is of that form or not. And for this, we observe that above here, we would call this the coefficient alpha. This is the coefficient beta, the coefficient gamma, and the coefficient delta, just by comparing to where these numbers appear in front of the different basis states. And now with these particular forms for these four coefficients alpha, beta, gamma, delta, we find the following relation, namely that alpha times delta is the same as beta times gamma, or in other words, the difference between these two different products is just vanishing. So this is the condition that the state in this composed system is separable. In all other cases, the system is entangled, and then we can use this difference to quantify the degree of entanglement, because all of these other states are the entangled states. And this leads us to the definition of the so-called concurrence, which is just a measure of entanglement between the two two-level systems. It's written as a curly or calligraphic C. So this is defined as 2 times the absolute value of this number, which would be vanishing for a separable state. Now this is defined in this way because this is in general a number between 0 and 1, where 0 of course then corresponds to the separable states, and 1 corresponds to the so-called maximally entangled states. And it is indeed easy to find examples of these maximally entangled states, and in particular there are 4 important ones, the so-called Bell pairs. So these are examples of these maximally entangled states, known as Bell pairs. And I'm first going to write them down in Dirac notation, because there the physical meaning is most obvious. They are denoted by beta naught naught, beta naught 1, beta 1 naught, and beta 1 1. And as I said, there are 4 examples of these, 4 cases of these. The first one being of this very simple form. And before I write down all the other ones, let me just tell you what this means physically. This is a situation in which the first system and the second system are always in the same state, but we have equal probabilities to find both of these combinations, probabilities of 1/2 to find these 2 combinations. And what is interesting about this is that when we know that our quantum system is in this state, and we do a measurement on one of the 2 parts, say the first one, and for example find that the state of the first system is 1, without doing any further measurements, we then know that the second system will be in exactly the same state. And the same applies when we do the measurements still on our first system, but obtain a 0. Then we will know without any further measurements that our second system is also in the state 0. And this also works for observations on the second part of the system. If we observe a 0 for the second part of the system, then without any further measurements, we know that the first part of our quantum system is in that very same state. However, these outcomes are still probabilistic. So without doing these measurements, we do not know anything about these states at all. So we have this probability, but it is completely resolved when we look at one part of the system. So therefore, there is a very strong correlation between the 2 states, but it is in a quantum mechanical superposition. Now, in order to work out the concurrence, maybe let me just translate this into a vector in which the only components that are finite are the ones in front of 0, 0 and 1, 1. So the very first and the very last entry. The entries that we called alpha and delta are just both 1/√2. And if we insert this here into the definition of the concurrence, this gives us 1/2. Beta and gamma vanishes. So we will indeed obtain 1 for the concurrence. So this is an example of a maximally entangled state, just as we wanted. Now the other Bell pairs are of a very similar structure, only that in the second version, the 2 states of the 2 parts are just opposite to each other. But knowing this, we can indeed infer what the state of one part of the system is when we know the state of the other part, say, through a measurement. And in the other 2 Bell pairs, we simply have superpositions, not with a plus but with a minus sign, but this is not changing the probabilities of these observations because the probabilities are obtained from the squares. So these are just other variants of these states. And indeed we can check that all of these 4 states are orthogonal to each other. So they actually form a basis of entangled states for our composed quantum system. Now let us return to the most general case of the density matrix given above. For a generally non-separable but also not maximally entangled state, just the most general form. But the density matrix can still be written in this block form of blocks A, B, C, D. And then the reduced density matrix of the first part of our quantum system, of the first two-level system, is just obtained by taking the traces of these 2x2 matrices. And similarly, the reduced density matrix of the second two-level system is simply given by the sum of the two matrices on the diagonal A and D. And with this, we can indeed write down explicit forms for these reduced density matrices for the case that our composed system is in a pure state. And I will give them here, but just for completeness. There will be no need to remember these at all. So all our constructions are what counts, but I'm just really giving these for completeness. So these are the explicit form of these matrices. Again, for a composed system that is in a pure state, otherwise we would have a sum of such terms. And again, just for completeness, there will be no need to remember these expressions. I'm writing them down here because we can use these to check some very general features. First of all, we see that the traces of these density matrices, row 1, just the sum of the diagonal elements in both cases, are the same, and they are just the normalization condition for our pure state of the composed system. So this will automatically be 1. So this corresponds to our normalization condition as we require in the most general case. And secondly, we see that these matrices are indeed Hermitian matrices. So when we transpose them, we keep the elements on the diagonal fixed, but they are all real in all cases. We interchange the elements on the off-diagonals with a complex conjugation, and we see that these off-diagonal elements, indeed in both matrices, are just related by a complex conjugation. So these are also Hermitian matrices. We can also use these explicit expressions to work out the purities of these two reduced density matrices. Now, this will initially be given by expressions involving many terms because we take the squares of these matrices and then the traces. But fortunately, these can be rearranged into a very simple form. Indeed, the two purities turn out to take the same value, and this is simply related to the concurrence of the system. Indeed, if the concurrence vanishes so that we have a separable state, the purity turns out to be 1. So the purity of these reduced density matrices is just 1, just as we discussed in the general case. So this is the situation when we can assign individual states to the two different parts of the system. These two different systems are essentially independent in these states. And if the concurrence is equal to 1, so we have a maximally entangled state, then the purity is equal to 1/2, which is indeed the smallest value that the purity can take for each of these two-level systems, because this corresponds to the case where each of these reduced density matrices is just 1/2 times the identity matrix. So we are in a maximally mixed state for these two different two-level systems. And this is the case in which we have the maximally entangled states. So the systems cannot be treated as independently, they are very strongly correlated. Now it is also possible to define entanglement between these systems when the composed system is already in a mixed state, but this turns out to be a bit more complicated. Indeed, the definition of entanglement for systems with more states or more quantum systems are active fields of research. But in this course, we are only going to need what I described here, the entanglement between two two-level systems when the composed system is in a pure state. Instead, what we are going to consider next is the concrete physical manifestation of this type of entanglement, which is associated with a very famous type of experiment.